with the hierarchical time stepping together, I will show you something like this. After we generate the mesh, we have to do an assignment of time step length to it. Here, we will say it in so-called hierarchical time stepping level. The lowest level has the longest time step, and it will use the least computational resource. So for this example, the outside has very large grid spacing and then very large time step, and they are represented by blue dots, which blue means that it will consume less computational resource. And then the time steps also half and half, and so it becomes smaller and smaller in each level. And for very high hierarchical time stepping levels, say this level 7, which is centered around Hong Kong, then the time step used in simulation will be the shortest. And then I will use color like red or purple to represent it, to visualize, to let user to visualize that actually when you simulate the whole group, these purple parts or red parts consume the most computational resources. So this is the idea. And then we can analyze the consumption of computational resource from this table, which we usually call the HTS table. So in this table, level means HTS level, with level 0, the coarser cells. So the resolution or described by distance between cells is large. And in this example, it is as large as longer than 100 kilometers. And then the column beside it, time step, you will see that the hierarchical time step assignment will assign a long time step to it. And this is the number of cells. So this is related to the area that use this cell spacing, and then dividing that area of the whole region with basically average area of each cell of this size, and you get the number of cells. And then you will see that this number of cells is using this long time step. So how much CPU core resource does this consume? You will see that it consumes very few computational resources. And so on and so forth, going from low to high HTS levels, you see that the grid spacing decrease, and then the time steps decrease. And as the time steps decrease, the computational resource consumed by that level becomes significant. So the numbers appear here depends on how you design your mesh very much. And about the last column, we compare the computational resource consumption using hierarchical time stepping versus without using hierarchical time stepping. As you remember, in lecture 2, we talked about if you use the open source MPass that use uniform time step, even for large cells, you have to use the smallest time step, which is less than 5 seconds, also putting to this cell. So the number of time steps you need to calculate become very large, and that will consume computational resource. So each layer, we can find out that if you use a very large time step, you save, wow, a lot of computational resource. And adding up and taking average, overall, you get the overall saving. In this example, CPAS will save 80% computational resource. That means CPAS use only about 20% computational resource if if you compare to MPAS. So for execution time, if you run MPAS and it costs 10 hours to run, then if you use CPAS, it costs about 2 more or something. Usually scaling is not perfect. Actual execution time will be a little bit longer than just playing the plain number here, but you can imagine that it is several times shorter execution time. So to visualize how the changing time step affect the computational resource usage, you can also put this number into a chart. So in this chart, the x-axis is number of cells in each HTS level. So if the area of using very short grid space is small, then the number of cells is small, then this rectangle will be thin, just like this example. But say level 7 is here, it has very high resolution and it uses DLT. So the y-axis is the computational resource it used relative to MPAS, in which you use uniform time step. So for the highest resolution one, they are the same, but you know CPAS has the buffer zone. It needs to pay the overhead. So actually for this HTS level, it consumes some overhead here more than MPAS. But as you go from level 7 to level 6, the cells are about 1 times separated 1 times longer, or the cells, the grid spacing is about 1 times longer. And then the time step used is also one times longer. That I mean that 2 DLT that become. Then the computational resource, if you do not count overhead, it becomes 50% number of cores because it jumps step. MPAS-A need to calculate 2 steps, but CPAS just use a twice as large time step, so it consumes half the computational cost, but it bears some overhead, so on and so forth. If it jump time step for using 4 DLT, then the computational resource is used will be 25% of cost relative to the way you use uniform time stepping, but you also add some overhead, so on and so forth. So you can compare the area. The area here, the gray area, is the computational resource if you use uniform time step MPAS-A to run the same simulation. But if you use hierarchical time stepping, then the area of the green bars adding together will be the computational resource consumed. So this is what you have done.